This reaction involves the addition of an alkene, and then we add H2 with platinum or palladium. You could also use nickel or something called Wilkinson's catalyst, and you make an alkane. It's pretty straightforward. You put a very small amount of this finely divided metal into your solution. It's a catalyst. It's heterogeneous because it doesn't dissolve, right? The mixture is just like a powder that sits in there. So it's pretty easy. What happens is the H2 that's floating around in solution comes over and kind of adheres to the platinum, and it does so as these little kind of like lollipops that sit in there, the little trees. The carbon-carbon double bond of the alkene comes and sits down with its pi bond like this, and then it lifts its leg up as it grabs one of these H's, and it's held in position so that the other H is thrown on there in a syn orientation. So just to give you guys an example of this down below, let's take a look at it. What if we had a molecule like that? Right, so if you take a second and draw that in, what you would see is this plus H2 and like platinum or something, right? And then what happens, and it's pretty straightforward, is that the H atoms get added to the same side. So there's one answer, right? So that would put your methyl groups in this case pointing back, but then we also get this guy here too. So that would put our methyls forward and our H's pointing back, right? So pretty straightforward. Just to do another little example down here below, what if we had something like that? We added H2 and how about palladium this time? It's the same deal. So H adds syn. So what that in the end, what that's going to do is that's going to put your bromo group either facing forward or going back. So right, we don't really care about this guy. That's not a chiral center. So we get this plus that guy, right? Your book kind of goes through showing how these add syn and rotating things around and stuff like that. But the end result is that you end up getting a mixture of stereoisomers. In this case, they are enantiomers of each other. Just as a little chapter 5 review, what's the relationship of these guys? If you said diastereomers, you're correct. And these guys are enantiomers. Now, the next reaction is actually fairly straightforward. In fact, the next two reactions are going to have elements that are similar to things that we saw before, especially with the octamercuration reaction. So this is the halogenation of alkenes. So as far as the reaction is concerned, again, you got your alkene here. Most of the time you're going to use chlorine or bromine. I haven't really seen iodine being used that much in textbooks, at least our textbook. So let's talk about what happens here. So this is going to be our nucleophile, right? So up to this point, we've had something act as the electrophile. But halogens they don't have dipoles by themselves because they're just X connected to X, right? Well, it turns out that the atoms, or the molecules, I should say, of bromine or chlorine can bump into each other. And when they do, they can get a temporary dipole that's been induced in the molecule. So what can happen here is something along these lines. Let's start off over on the side here. So we can get a bromine and a bromine, right, kind of bumping into another bromine atom. Right, so that bumping in can cause this transfer of electrons a little bit where you get a delta plus, a delta minus there. And then that corresponds to delta plus and delta minuses on the other ends here too. So we just need to know that there's a slight delta plus on one end and a slight delta minus on the other end. often enough that this reaction will occur. So because, remember, we're reacting with the p orbital of our pi bond, we have to consider this top-bottom approach. Now, we're going to form a three-membered ring here. So let's come over here and continue this thing, and let's look at what happens as we do what we'll call here a top attack. So electron flow looks something along these lines, and let's put our electrons in here. And then let's put our delta plus in here, or delta minus on that end. And remember, they're bumping into each other, so that's where that's coming from. So this is coming over here, making a bond with bromine. Right, that's kicking off bromide. Set of electrons coming over here, making a bond to a carbon atom. Okay, you're going to get a three-membered ring. Now remember, this side, that carbon that I'm bubbling in right now, it's more substituted, so it can handle a delta plus charge better. So as we write this thing out, you got your carbon and your carbon here. And let's put all the basic stuff in right now. Ethyl, H, and H here. And then you're going to get a bromine in here. It's a bromonium ion, or sometimes they call them halonium ions. And the bromine's going to be kind of hanging out more, leaning a little bit more towards the carbon that has more H's. So that's what I'm trying to show here. And this thing is going to look weird because bromine is going to have a plus charge on it. So you're going to get a nice delta plus here, a little bit of a delta plus right there. And again, remember, that's a bigger delta plus because of the ethyl group being able to kind of donate inductively electrons to that carbon. So it can accommodate that a little bit better. All right, so you got bromine in here. So notice we kicked off bromide. So now bromide acts as the nucleophile and three-membered ring. So remember, when you have a three-membered ring, we always attack from the backside. So we're going to come over and we're going to do this, and we're going to end up getting that anti-arrangement. So then I always like to think of this as there's my bromine, there's my carbon, and there's my other bromine, and then everything else, right, just stays on your wedges and dashes. So you got your ethyl, and then right, everything else is just H's in this case. H and A. All right, so there's one of your products. That's one. Okay, now we form the other product too, because there's no reason why it preferentially wants to add just to the top. You could go to the bottom also, right? So as we go through and look at the bottom here, right, bottom, and I'll just continue this down. That's another Br2 collision, right? So we still have our lone pairs in there, delta plus, delta minus in there, and we still see that same flow of arrows. I don't think I'm going to draw them in here because I don't want to complicate the way that picture looks up above. But when we draw this down at the bottom, we end up getting our carbon, right? Put in all your other groups. Let you guys catch up a little bit. So what do we have here? An H, an H, an H, and an ethyl. All right, now this is going to have that same kind of slant to it a little bit. So we'll draw it like this. So some textbooks won't show this perfectly, and it's hard to show really, right? So you get your plus charge like that. Same idea. It's up above. Bigger delta plus here, smaller delta plus on that side. And bromide comes in and attacks this thing. Three-membered ring, so coming around here and doing this. And then again, what I like to do is just, I like to put my bromo group in. Right. Leave those in plane. And then, as we kind of said before, everything else just kind of falls into position. So then you end up with, what do we have, an ethyl there. an H, and then an H, and an H. All right, so you get a mixture of two products here. These, in this case, these two products, they are enantiomers of each other. So the other thing that we use this for, it's a neat test that we use for qualitative analysis, and it tells us whether or not we have a double bond present in our molecule. So it turns out that if you take a test tube that has like a liquid alkene in it, most of these things are going to be colorless, and you add bromine to it. Now bromine is going to have kind of a brown color to it. It's kind of orangish, actually. Brown, a little hint of brown in there. But anyway, when you add these two things together, and DCM is dichloromethane, that's CH2CO2. This is just a solvent in this case. You get a halogenated alkane, but the bromines reacted and the solution becomes colorless. So that with that brown color, you get a colorless solution. Interesting side note here, not all double bonds are equal. So this molecule, right, which is benzene, has double bonds in it, and when it reacts with bromine, we still see an orange kind of brown solution there. Can anyone think about why that happens? Why the double bonds in benzene don't react? Well, remember that these double bonds are in resonance, right? So when we draw the resonance structure of this, if you guys remember doing all this in class at the beginning of the semester, you can move around and they could do this, right? So there's not really a double bond there. Remember, it's like there's, rather than 3 singles and 3 doubles, it's more like you have 6 1.5 bonds, essentially. So there's no reaction here. So we maintain that double bond alternation kind of pattern there, okay?